Good morning, everybody. Thank you very much for inviting me. As I was preparing this talk, I was thinking this probably maybe the last time I'm actually invited to give a talk only on this source, because now there are so many repeaters. It's becoming not quite so novel anymore, but I'm very happy about this fact, so don't get me wrong. Vicky already did a lot of the intro, so I will fly through the introduction of some of the history of the source. I will then go a little bit more into our in-depth radio monitoring. Many of the properties of the source are time variable. And then I'll talk a little bit about some of the models that we've been thinking of, and hopefully getting insights from all of our theorist colleagues here. So first repeating FRB 121102 was originally discovered in archival data from the P alpha survey taken at the Arecibo Observatory. Shortly after we discovered the first burst, we went back and did follow-up observations and found an additional 10. We now, again, this is sort of my very brief summary of all of our follow-up. I like to think of this source is now sort of a system. It's no longer just sort of a mysterious object. The system composed of three parts. One is actually the still mysterious source of the bursts. Where's my green thing? There it is, the bursting source. This has been localized, I'm gonna use a stick. This green dot is confusing me. So we have the bursting source. It was initially localized about milliarc second precision by the real fast team using the very large array. We then stepped this up and we used the European VLBI network to get sub-milliarc second localization. Once we had the VLA localization, we discovered that at that point on the sky is a compact persistent radio source. We then again went to the EVN and were able to show that it must be smaller than about 0.7 parsecs. Note, this size is actually limited by scatter broadening, so it could be smaller. So there's an upper limit to the spatial extent of the source, and it is spatially coincident with the bursting source. And of course, on the largest scales, we have the host galaxy. Turns out that it's at a redshift of about 0.2, which, as Vicky mentioned, is consistent with the dispersion measure distance, roughly. It's a low metallicity dwarf. Now, going slightly more in detail, I'll start with the big scales. As I said, host is a low metallicity dwarf galaxy, 10 to the 8 solar masses of stars, a fairly high star formation rate. Furthermore, so this is the HST image. This blue circle, oval, shows the optical extent of the galaxy. So it's about 6 kiloparsecs in diameter. Here, this pinkish circle shows us then the optical extent of a large H2 region in this galaxy, and this little white plus or cross shows the position of the bursting source and the compact source, of course. So this bursting source is located in a star formation region, which is almost certainly telling us something important about its origin. In the persistent radio source, we've been monitoring its flux density since the localization that's shown here. So this is flux density as a function of time. The black points, this is with the VLA. Sorry, I don't think I mentioned this, but this is with the VLA. The red triangles show when we have bursts. There's no correlation with changes in the flux that occur when the bursts happen. We do have some more recent data, but my colleague Robert Wharton has not yet processed it. It's fairly new. And all of the variations you see are consistent with refractive scintillation. And here I'm showing then a radio spectrum of this source. There's perhaps a break around 10 gigahertz. Now going a bit more into the bursting source, is a nice gallery of what we like to call our so-called weird bursts. They are now not so weird, given that all the other repeaters seem to show very similar structure. Nevertheless, at the time, we found them to be weird. So here I'm showing the ones boxed in red are from Arecibo. The one boxed in cyan are from the GBT. These have all been coherently de-dispersed. They were purposely chosen to be bright to nicely show the structure. They've all been coherently de-dispersed to a value of 560.5, and most of them show this wonderful sad trombone structure, which I also think is a fantastic way of describing this sort of downward drifting subpulses. These little red ticks show where R5 has been excised. So this sort of structure here is real, but these sort of very narrow band, sort of dimmish channels is actually due to the fact that we've had to remove some due to R5. That's all about that. So also quite remarkable about the source is it is 100% linearly polarized. This is shown here. Here are two examples from Arecibo and two again from GBT. So these are dynamic spectra. Here are the polarized profiles. So red indicates the linear polarization. What I think is also quite important is that the polarization position angle is flat across all of the bursts. And if you look closely, it's actually fairly, the value itself is also fairly consistent from burst to burst, which is almost certainly telling us something extremely important about the emission, or the source itself. It tells us something about the orientation of the magnetic field on the sky, which seems to be constant both across a single burst and seems to be reasonably constant across large stretches of time. Something that many of us have been looking into more recently is trying to investigate the energy distribution, so this is energy burst statistics of the source. Here we tend to publish in terms of the cumulative burst energy distribution. So here we have e to the beta. The recent results show that beta is around sort of minus 1.7. And here are three recent results that came out. They're all nicely illustrated or summarized in this plot from Lena Ostrom's paper that was on Astrophysics earlier this year, different colors of the different telescopes. Noticeably, for example, Arecibo and Kelly's paper from early this year probes a very low energy range, because Arecibo, of course, is a very sensitive telescope. In this particular paper, they're publishing results from Aperitif, which is the phased array feed on Westerbork, which then probes, again, on the other hand, a higher energy range. And then, of course, there are several experiments in the middle. And interesting, they're all reasonably consistent, in particular, Arecibo and the Aperitif are definitely consistent within the errors, and they are, in fact, probing very different energy ranges. We have there's a PhD student in Bonn who's working on a similar results, similar analysis with bursts from Effelsberg. We get a slightly slightly shallower slope, and we're probing an energy range sort of here in the middle. But this is preliminary, and nevertheless, they're all, I'd say, roughly consistent. I would point out that there's an earlier paper by Casey and collaborators, which used various telescopes at various frequencies and found a somewhat shallower slope. There's a good chance that this has to do with the fact there are too few bursts to properly consider completeness. Considering completeness is very important because at some point your distribution sort of ticks over. You can see it kind of nicely here, or here it flattens out, simply because there's an energy below which you can't detect all bursts. So one very interesting feature of this source is that there's significant time variable properties. I'll start with dispersion measure variations. So we're now fairly confident to say that we have certainly measured increase in the dispersion measure of about 4 units over the number of years since we first discovered the source. So here's the dispersion measure as a function of MJD. This was the discovery burst. This was then the collection of new bursts from Arecibo. Their yellow points indicate data which was not coherently dedispersed, which is important because it could be that you're dedispersing structure into your value. That's why I have them in a different color. There's another one notably up here, which is also incoherently dedispersed. All of the blue points are then coherently dedispersed. So there we can clearly see the burst structure and take care of it when we do the dedispersion. And you can see that the value sort of in 2016, 2017 had gone up to about 565. And then recently, somewhere, at least starting at the end of 2018 to now, it's gone up to something closer to 563 to 564. It would be very nice to obviously fill this gap, and we're trying to find some detections in between there to see whether it's actually a gradual rise or a jump. That would, of course, be very interesting. Fortunately, at the moment, we can't say. Perhaps more remarkably is the massive decrease in rotation measure that we've been observing. As Vicky mentioned, this source has an extremely large rotation measure. When we first measured it, it was just over 100,000 radians per meter squared in the observer frame, so it's correspondingly higher if you convert it into the local frame. It then dropped down to, by sort of spring of 2018, it dropped down to almost 70,000. So for most of you, this is probably the last time you saw this plot. Would have ended about here. Middle of last year, we have a few more detections, and surprisingly, they hadn't actually dropped by that much compared to what the previous drop was. So they're now about 67,000 radians per meter squared. So now I'm going to sit back, talk a little bit about the models that we've been thinking about for the source. So in the original localization paper and the suite of those papers, we suggested 2 models. One, or or indicated two possible models. One is a sort of millisecond magnetar wind nebula model, which many people in this room have really worked very hard on, so I won't go into too much detail about this one other than to say the idea is that something like a decade ago or a couple decades ago, a transient event such as a superluminous supernova or a long gamma ray burst occurred. There was a millisecond magnetar born. Today, that magnetar perhaps could be generating the bursts in the magnetosphere or perhaps in the ejecta itself. And then the persistent radio source is then the sort of the expanding ejecta, shell of ejecta. The other possibility is that we have something, perhaps an energetic neutron star, perhaps the AGN itself, in a low luminosity active galactic nuclei in this dwarf galaxy. In this case, the persistent radio source would be the AGN itself, and the bursting source would be whatever the bursting source is. I'm also running a little behind, but I have sort of a list of sort of evidence that we have, and generally speaking, whether it's easily explainable or less easily explainable by the two models. Very quickly, the source of luminous bursts arguably is very natural in Model 1. And Model 1 is also easily explainable with the location of star formation region and, of course, the host galaxy properties. The fact it's a low luminosity dwarf is consistent with known hosts of superluminous supernovae or long gamma ray bursts. On the other hand, we have the strong spatially coherent magnetic field. Observationally, we see that generally in accretion disks of AGNs. Also, the luminosity, or the existence and the luminosity of the persistent radio source, and in particular, luminosity, is very much consistent with AGNs, but is order of magnitudes larger than known, at least galactic supernova remnants or pulsar wind nebula. So I'm not going to talk about Model 1, because like I said, there are plenty of experts who will be giving lots of talks about this. So I'm going to focus more on Model 2, which is the low luminosity AGN. I want to give a brief aside, which is to point out that some of this sort of sad trombone structure that we see is very similar to a flavor of crab giant pulses, particularly the high-frequency interpulse giant pulses, which show this lovely banded structure, and the separation of the bands increases linearly with frequency. So here, there's banding, and of course, in our source we see both banding and drifting in time, but I want to point out that there is an interesting analog. Also, the polarization properties of these giant pulses are very similar to what we see. So again, let's go back to specifically the low luminosity model. There's an interesting sort of analog in our own galactic center, and this is one of the reasons why people, I think, take this model reasonably seriously. So here's a map. The background picture is a radio image of the galactic center. The white dots show the so-called galactic center pulsars. Importantly, is 1745 minus 2900, which is the so-called galactic center magnetar. It's a radiolog magnetar with a projected distance of only 0.1 parsecs from Sagittarius A star. We've been monitoring the source with Effelsberg since it turned on in 2013, almost 7 years ago. And it is, the only known radio pulsar which shows that also shows significant rotation measure. So it has a very large rotation measure of, actually the repeater is now getting down to this level, so they actually have similar rotation measures now. And it also has significant variation, although not quite at the magnitude that we see. But nevertheless, it's an interesting analog. I also want to point out a paper that came out earlier this year by Amy Rines and collaborators. She did a large VLA survey looking for compact radio emission in a sample of dwarf galaxies. I won't go into the details. There's 111 targets, and 13 of them they claim to be solid AGN. The radio sources are definitely AGNs. And they point out, interestingly, that the majority of the AGNs that they see, so a little over half, are in fact offset from the optical center. So if, in fact, our host happens to have an AGN, which admittedly is still rare for dwarf galaxies, it is not strange that the AGN isn't offset from the center. So this is quite an interesting result, and I've shown, just to illustrate here, again, our HST image and the fact that if this is an AGN, like I said, it is offset, and that's in fact not strange. So this is just in time. Here's my very brief summary. 1211-2 is now only one of many repeaters, but nevertheless, because it is the first discovery, it was discovered 3 years before the next one, we have the longest baseline of temporal observations. It exhibits many properties shared with the new sources, including this complex time-frequency structure, so the sad trombone features, very high linear polarization, and actually the flat polarization angles has also been seen in at least one of the chime repeaters. And we are still continuing to monitor for temporal variations in DM and RM, as well as the flux density of the persistent radio source. And I think we're all very interested to see whether or not this source is in fact typical for repeaters, or if this is sort of the oddball. But yeah, thank you very much for your attention.